Today, today I explain the part 3 of public a public platform for virtual IoT based monitoring and tracking of COVID-19. Let's start. In section 4, SDNC centric tracking and real-time information services. The plat- proposed platform is using centralized approach based on the SDNC. However, the CDS perspective, it's a decentralized method. This section offers a new way of linking SADB settings between CDC and SDNC, and how the centralized SDNC collects the information from distributed information provider around the world. In addition, it proposes a way to receive information from the information consumer perspective in a real time. Section 4.1, associating SADBs between CDC and SDNC. This paper uses 120-bit Diffie-Hellman key to give each CDC up to 1 to the power 128 keys under its management, considering the possible total number of keys where each CDC uses different set of global parameters for Diffie-Hellman key exchange. Scalability in this space of key can be granted, covering through numerous covering through enough number of worldwide CDC as well as large number people manage each CDC. If a CDC control and virtual IoT nodes, the CDC needs associated N Diffie-Hellman keys with SDNC. However, these Diffie-Hellman key exchange do not happen at the same time. In addition to each Diffie-Hellman key exchange between CDC and SDNC does not require real-time process. As shown in figure 3, CDC and SDNC wish to exchange a group of keys. Here the total number of secret keys, that is N, is equal to the number of people CDC needs to manage. First, CDC selects N random integers to make secret value table of CDC and gives SVTDs of S, SDI1, D1, SD2, SD2, and S till SDN, and computes the and corresponding blind values to make blind value table of CDC, which is given by YDT1, YDT2, YDT2 till the YDTN, where YDI equals to AXDI mod QI equals to 1 2 3 to the N. But then the CDS sends as associated request with the information of the identifier. This information is like case 1, case 2, case 3, and till the N to the SDNC. Receiving the request of SDNCs selects N random integer to make the secret value table of the SDNC, which is given by SX1, SX2, SX2 till the XX1, and computes the N corresponding blind values to make a 1 2 3 till N. After associated process, it is computed between CDNC and SDNC. They exchange their BVTs. As a result, CDC and SDNC maintains their SADBs. Each SADB's entities is identified by CDC side blind value, that is the field of virtual IoT node. This is the figure 3, which shows the associating Diffie-Hellman parameters between CDC and SDNC. Section 4.2, updating a RR in RRDB at SDNC. Sorry. If SDNC considers that it is necessary to track a particular person, it assigns a personal three integers, which includes identifier of the number in case I, CDC side secret value XDI, SDNC side blind value YSI to the virtual IoT node that belongs to that person. When the virtual IoT node receives this information, it computes its identifier, that is CDC's side value, by using equation YDT equals to AX DI mod Q. Now, virtual IoT nodes begins to maintain its SA record. Note that person's identifier, that is KSI, is independent of the virtual node. Then virtual node computes its key as KDI equals to YSI power XDI mod Q. This key is used to encrypt the ID field of its RR as well as the update message RR to SDNC. The main role of this virtual IoT includes the track I, its location related to status such as current IP address, second GPS data when it moves. As a result, virtual IoT RR is always up to date because a person moves with his phone. Each virtual node is responsible for sending an update RR message to SDNC when there is any change in its RR. When the SDNC receive update RR message from a certain virtual node, a real-time Diffie-Hellman key computation is necessary to compute the corresponding DH key. As shown in figure 2, when any change in virtual IoT RR occur, the virtual IoT node sends update message to SDNC. This message contains the safe part encrypted with CDC side key of KDI, that is EAES, KDI, YDI, KSI, IP case, GPS KSI, as well as RR message. In addition to the blind value of YDI, in that message has no relation with the person who owns this blind value. Receiving the update message, SDNC first searches SDNC secret value corresponding to its value of YDI from its SADB. Then SDNC computes the Diffie-Hellman as KSI equals to YDI x SI mod Q and carries out AES decryption process of DAES. Using the SDNC side key, the decrypted value YDT equals to blind of value of YDI in the message. Now SDNC updates YDI index entry in its RRDB. This is figure 4, which represents the updating an RR in RRDB at SDNC. 4.3 subsection querying RR matched with index list. CDC obtain the necessary data from RRDB at SDNC via query reply mechanism like DNS. When CDS sends the query message to SDNC, it uses the index list that sends for combined list of word such as location information, type of person CDC wants to observe. When the query message arrives at SDNC, it searches to find RR related to the requested index list. Figure 5 shows the example case that query the match to RR, YDI indexed RR, and YDK indexed RR. SDNC sends to RR to CDC as a reply message. Here, SDNC finds information CDC is looking for from RRDB and answers to it without processing it. Now the processing significantly reduced SDNC computing load to handle queries and replies, and also reduces the amount of time spent on query replying trying to Try from SDC viewpoint. When SDC receives the reply message, it first calculates the relevant keys. Using these keys, the SDC can decrypt the encrypted value in the RR. Now CDC analyzes the replied information. This is figure 5 representing the queuing RR matched with the index list. 4.4 RR or accessing the RRDB from the normal user having no security associations. According ordinary users do not maintain any security association. However, they can access necessary RRs from the RR from RRDB at SDNC. Those users send those users uh, send the query message to SDNC with the index list containing the location information. When the query message arrives at SDNC, it searches to find RR related to the requested index list. Hence, here SDNC replies in the same way without discriminating CDCs and ordinary users of query or of queuing query center uses as a query center. Figure 6 figure 6 shows that the example case that query matches to RRs YDX and associated RR. Here SDNC finds the information the user is looking for from RRDB and answer it without processing it all. SDNC sends these two RRs to the user as a reply message. Receiving the RR, the query sender neglects the encrypted field in the received RR. Now it starts to analyze the content it in all cleared areas in RR. This shows the figure accessing RRDB from the ordinary user having no security associations. It's 5.14 section quality of service at latency. DH algorithm uses the computation of modular explanation that is the only reason to cause a latency problem. From the viewpoint of security management, to generate the BBT, CDC, and SDNC, each needs n times required to compute unit modular explanation. However, the completing BBT does not require real-time operation, so the computing load of this degree is not a problem in a latency aspect aspect of the DH keys exchange. As long as the authentication check goes completed, update RR message from virtual IoT node are registered a new identity RRDB or update the changed identity content without any processing. Therefore, even if the amount of n into P increases, the SDNC side latency does that occurs. The RRDB content is not a problem. When SDNC receives a query RR message, it searches the relevant RR that match with the index list requested and acknowledges the matched RR without any processing. such as encryption and decryption. So even if the amount of n into p increases, as SDNC side latency that occurs to handle worldwide query reply tries is not a problem for CDC and ordinary user who receive a reply RR message. The time it takes to complete the query and reply procedure can decrease considerably. Because of the same reasons as mentioned above, we built a testbed to obtain a latency data that that explains how much it takes to complete the updated RR procedure and computes the shared DH keys in real environment. In a test bed in figure 7, SDNC subnet link operate over a Wi-Fi with the data rate of 72 MB, and the update RR procedure takes time to complete the DH key agreement between peers. So these latency consists of round trips, network delay, and DH keys computation, while the round trip delay relies on network traffic condition. The DH keys computation time mainly depends on DH keys size. In addition, DH keys computation time varies depends on update RR request rate, as shown as table 1. This paper considers two conditions: CPU condition of 1 and 2. CPU condition 1 assumes that smartphone's CPU is powerful free when almost free when update RR request. The CPU's condition 2 assumes that the computation smartphone's CPU power is already occupied by other update RR request by 35% when update RR request arrives. Our testbed runs the web application where virtual IoT nodes send HTTP request in. It contains the safe part encrypted with CDC side key of KDI, then that is AES KDI YDI case 1 IP case GPS case, as well as it builds the value of YDI in clear form. As SDNC receives HTTP request, it first searches the SDNC side secret value corresponding to build a value of YDI from its SADB. Then SDNC computes the Diffie-Hellman keys as KSI equals to YDI X XSI mod Q of value from its SADB. Then SDNC computes a Diffie-Hellman key as KSI equals to YDX X mod Q carries out the AES decryption process of DAES KSI, which gives AE, AES KDI YDI KSI IP case GPS KSI. Using the SDNC side key of KSI, the SDNC authenticates the update RR message by checking if decrypted value of YDI equals to blind value of YDI in the message. Then SDNC updates YDI indexed entity in its RRDB and sends the update OK message to virtual IoT. The sends SDNC playing server computes the Diffie-Hellman key. We deal with our four different keys: one 12-bit, 1024, 2048, 3072-bit key. Virtual IoT node uses CPU core clock in 1.2 GHz and Android version of 5.02. SDNC carrying a web server operates with CPU core of 2.9 GHz. We repeat HTTP session 20 times each. Each defilement key obtains the latency order and NDH key computation. So the delay from departure of updated request to the update OK arrival includes network delay and Diffie-Hellman key computation time. Figure 7. The setup testbed to obtain experimental data that computes virtual IoT that completes the updated RR procedure in a real world environment. Figure 8 shows the experimental data that explains how long it takes for virtual IoT to complete the updated RR procedure. The measured latency includes the two main factors of the network delay and the computation delay. It shows that latency results differ a lot depending on the DH size. If the DH size increases to 1028 bits, latency reaches to 1 second. For DH keys of 3072 bits, it approaches 10 seconds, as shown in lower graph. Latency variations increases as key size becomes large. Considering that virtual IoT based monitoring platform uses 128-bit Diffie-Hellman key, latency requirement for this should be satisfied enough. Figure 9 shows the experimental data that explain the DH computation time under the CPU condition 1. DH computation delays differ a lot depending on DH key size. For the DH key size of 3072 bit, the key combination delay approaches 10 seconds, where the component of network delay has no effect. As lower graph, shown in lower graph, latency variation increases as the same as the size becomes large. Considering that DH key computation delay decreases below 100 milliseconds for the 120 for the 512-bit DH key. Our virtual IoT-based monitoring platform, which uses 128-bit DH key, satisfies the requirement DH key computation latency. This shows the graph of in figure 10 shows that how DH computation differs as the updated RR request rate varies. It it is shown that DH key computation latency difference between CPU condition of 1 and 2 becomes more considerable as key sizes increases. However, differences can be negligible for case of 512-bit Diffie-Hellman key. So it can be concluded that our virtual IoT based monitoring platform, which uses 128-bit Diffie-Hellman key, satisfy the requirement of DH key computation latency even under the condition that computing power of 35% is occupied with handling the massive update RR request. Figure 10 shows the latency to compute shared Diffie-Hellman key under condition 2. Thank you.